All right, welcome everybody. Let's get started. This session is on getting started with real-time analytics. I'm Rahul Bhatia. I'm a solution architect with Amazon Web Services. And joining me today is Kandarp. I will have Kandarp introduce himself.
I'm Kandarp Shah. I'm engineering manager for data platform and game services team at Guri International.
Thank you, Kandarp. So with that, let's just do a quick run through to the agenda. Today, we're going to take a macro level of the two main streams within data real-time analytics. We'll look both at the data ingestion and the data processing. Later, after that, we'll have Kandarp walk through Guri International and their architecture on a real-time analytics on AWS. He will also share some of the lessons they learned while building the architecture on AWS and some of the key takeaways as a part of this talk. So if you look at the two macro level of real-time analytics we described, the first being real-time ingestion of data, collection of data, and second, the processing of data. Both these two macro levels have quite some key semantics in there which are parallel to each other. If you look at it on the collection side, while you need a collection system which can scale to collect data from thousands or hundreds of thousands of sources, but on the same processing side, you need the processing systems to be able to scale up to keep up with those events as they're flowing into your collection system. Not only your collection system needs to provide you a durability of data, so once you write in there, you are certain that data is going to be available for you to process. On the other side, your processing system needs to be able to recover from failures in case. They need to be able to do a checkpoint, so to say that you have processed till this date or this records. In case any failure happens, you can resume from there on without any hardship on your part. They both need to support the concept of elasticity. As you know that your data flow rate or data processing rate is not going to be the same throughout the whole time. It's going to scale up and down as the number of users. For example, in a website, the traffic on your website is never going to be the same throughout the 24 hours. It's going to change depending on a certain lot of factors. And you need to have a system which can scale based on the patterns of the traffic your website or your collection system is facing into. And the lastly being, there's a concept of a data bus as architecture, where what you have is your data source producers do write a data into a single system at once, but you can have multiple streams of data processing happening on the other side. The multiprocessing could be, for example, you're doing real-time monitoring using simple metrics. Could be that you're doing a machine learning, a deep learning with that data set. You're writing that to some SQL store for doing some operational monitoring, and etc. The idea being that once you write the data, you wouldn't have to replicate it to multiple places to do the processing for different paths or different mechanisms. So with that, those two processes described, or those two streams described within real-time analytics, let's look at the pattern of data ingestion first. So within a data collection, imagine that you want to build a website which just shows you from some stream of records, top 10 records. Example being, let's say that from a website, you want to know the top 10 referrers to your website, people who are coming to your website and how they're being referred to your website. On a very simple design, what you could do is you could build basically a web server. The web server is collecting all the clickstream logs, does all the processing, and finds the top 10 and displays it to you back in a graph or something of that sort. It works for a small, if your website has a small thousands of few users, maybe it could work. But what if it grows out to hundreds of thousands of users or millions of users? At that point in time, you could look into something like partitioning your data set. So what you do is you build another fleet of servers before your web servers, and what these boxes, the orange boxes are doing here, they are collecting your data from your producers. They're doing a computation on top of it to figure out how many records or which are the top producers or two top referrers in there, and sending them back to your website or your web server. Your web server at the same time is now taking the records, computing from all the records coming in from different boxes, computing the local or global top 10 and displaying it back to your users. So now each of these boxes is doing a computation. So your work is a little bit distributed. Yet there a problem remains in there that if you look at the lines, colors of the lines which are going from your data sources to the boxes, they are random in color. So each of these boxes don't know which group of records it's getting from, whether the referrers are coming from Google, from Amazon, from somewhere else. They have no idea about who's the referrer to these websites. So they cannot do a computation of top 10 only. What they can do is they can do approximation of something, saying that based on million of referrers, here are one record per referrer, and hey, web server, can you compute the global top 10 now? Which still means that your website has to deal with some kind of computation which it shouldn't have to in the first place. So how do you really solve that problem? Well, it turns out what you could do is, if you had in between a data broker service, and imagine what the data broker service does is, it ingests the data at scale, and on the output, it sorts the data based on some group or based on some partition. And now each of your orange boxes can do a computation. So to compute top 10, all of these orange boxes have to do is they have to send only 10 records back to your web server. And in this case, for example, being 3 boxes, your web server needs to process only 30 records, which is better than solving a 3 million record problem or 100 of millions of records problem. So now, in this architecture, your data is coming ingested. There's a central data broker, which is basically ingesting the data, providing a sort of buffer. Within that buffer, it's sorting the data, so your processing boxes can take the data set in a certain order or by a certain group, do the computation, and send the data set back to the web server. So now your web server is basically just doing the idea behind what it is doing is to display the data records. Out of 30, displaying the top 10 records back to users. It turns out that central blue box is what Amazon Kinesis is. So Amazon Kinesis is basically a service, a managed service, which can allow you to ingest data sources or data streams in real time from hundreds of thousands of sources. And not only that, it can allow you to stream data up to terabytes per day. So you can ingest that much of data sets within an Amazon Kinesis from hundreds of thousands of sources. But it also allows you data to be processed in the manner we spoke about earlier. And logically speaking, a named object within Kinesis is a stream. A stream is something in which you put data onto. A stream is a collection of something called shard, a shard being a basic unit of capacity within a stream. So as number of shards within a stream grows, your stream has more capacity to read data or to process data. The one thing which determines that where the records goes within each shard for the given stream is something called a partition key. Think of partition key as something a way you can distribute your data across multiple shards. So if you have, for example, let's say 10 shards within a stream, you could say that my partition key going be number be 1 to 10, so which means the number partition key 1 is going to, let's say, shard 1, and the partition key number 10 is going to shard 10. It's just a simple illustrative example, but the idea being a partition key is something natural which can help you distribute your data across multiple shards in a stream. Then you have something called a record, which is basically like, think of something like a clickstream log, a tweet. These are all a single record which goes within a stream. And whenever you put data within a stream, what Kinesis gives you back is something called a sequence number. And that sequence number, which is generally increasing within a given partition key, is that what you can use for doing checkpointing, for doing replay, for doing failure recovery, and etc. Because that's a number which is increasing, so you can create a simple checkpoint saying that I have processed my data till sequence number 10. So next time, if your process fails or anything happens, you can start resume your process from sequence number 10 onwards. What Kinesis also does is once you do put data into Kinesis, it stores or it gives you the ability to read your data for a period of up to 24 hours. And you can have multiple processes read the same data set over and over again. So you could build a multiple processing platform. So once you put data into Kinesis, it's available for you to read up to 24 hours. And that means now you can have multiple readers reading out of it. For example, doing work like data archiving into S3, which is our object store. Data archive, metrics, real-time metrics into DynamoDB, which is a NoSQL store. Or they can do operational metrics back into Redshift, which is our data warehouse, a petabyte scale data warehouse. Or you can even write something like EMR to basically do machine learning on top of the data set being written in S3. So with Kinesis, the idea of central data bus basically becomes as a part of a collection process of data. Once you write data into Kinesis, you could have multiple processing applications which can take the data and process it using multiple paths. And the way Kinesis allows you to do it is by something, as we mentioned, something called shard. A stream being a named object and a shard being a unit of capacity. What each shard gives you the ability to write data at the rate of 1 MB per second or 1,000 transactions per second, which means that either of which comes first, that's the limit of a shard is. So you can write up to 1,000 transactions or 1,000 records, or you can write in collection up to a megabyte per second. On the read side, what it gives you ability is to read at 2 megabytes per second or 5 transactions per second. What it means that on a single shard, you could have up to 5 processors reading data out of that shard and each reading the data at the speed of 2 megabytes up to 2 megabytes in total. And how you scale up and down your shard is the elastic part of the Kinesis is by two API operations called merge shard and split shard. The moment you call a merge shard, for example, a pair of shards become one single shard. And since you're charged by shard hour and your capacity also is determined by the shard, you elastically scale based on the number of shards in a given stream. If your data is going to grow, you can call a split shard, which is going to give you from one parent shard, it's going to give you two child shards. And now you have double the capacity of the single shard given before that point in time. Sorry. And data is, again, as I mentioned before, is available for you to process up to 24 hours once you do a put record back into Kinesis. And now you can basically use anything to do that data within the 24-hour window, which could be archiving it, processing it, or any of that pattern. So imagine that now you have two producers in your applications. Each of these two producers are producing records at 2 KB of size, but at 500 transactions per second. And if you want to stream that data set into Kinesis, so how are you going to size the number of shards in your Kinesis stream? So it turns out since each stream or each shard gives you ability to write data at 1 megabyte per second, and you have roughly two producers here, both of them producing at the rate of 1 megabyte per second, cumulative of 2 megabyte per second. So you can have two shards basically here. And at the other reading side is going to give you ability for have two applications which can read data out of this. Because you're putting 2 megabyte per second total in the stream, two shards are there, and each shards give you 2 megabyte per second of read, so total of 4 megabytes. And each application has to read at least 2 megabytes per second, which leads to 4 megabytes per second as a number in there. So in this case, two shards are enough for you to start processing. But what if you need a third application to read now? That idea being that on the other side, your get is remaining the same, your read is remaining the same, sorry, your write is remaining the same, but your read is increasing to have one more application now. In that case, what you could do is add a third shard simply. So at the moment you add another shard in there, now your read capacity has doubled, so which means that while your ingestion is still maintained at 2 megabytes per second, your reading now can be at 6 megabytes in total, so which means that three applications totally can read 2 megabytes each. So it can, all three can process the entire data set which you have been put into Kinesis stream. And that's the pattern based on which you can elastically scale a Kinesis stream. So to recap, we talked about on the data ingestion side that how Kinesis helps you move from a batch-based processing into continuous ingestion of data. Not only that, how it can elastically scale up or down based on your workload or based on your ingestion patterns. That workers can replay the data up to 24 hours. Once you do a single record, that record is available to be processed up to 24 hours. And you can scale up to gigabyte seconds or terabytes per day without losing any durability, because what Kinesis does is automatically writes data into multiple availability zones once you do a put record within Kinesis. And finally, you can run multiple Kinesis applications, because the way it is designed that each shard is designed to fan out your reads, so you can have multiple applications processing the data set out of that stream. Now we're going to move on to the data processing side of things, that once we have data being collected in Kinesis stream, assuming, and you have been able to collect data at scale, what you're going to really do with this data set. Because real-time actually is a platform, it's just not collection. You have to figure out something to do with the data set also. A very common architecture what we see in general is around data streams is people use different stream processing systems, such as Kinesis client library. We'll talk about that in a moment. Spark streaming, Apache Storm. They use all of these stream analytics process to basically get real-time counters, real-time metrics, and put them into some kind of delivery, be it via notification via APIs, SNS, be it via dashboards, alerts, or etc. And at the same time, it is quite important that you build a layer which can take data from a stream and archive into something like S3 for that matter. Why? Because eventually what you're going to come to a point where you need to restate something, where something might have failed or something might have gone wrong in your real-time system. With having that data archive ability, it gives you the ability for you to restate what was gone wrong, or reevaluate your understanding as you understand your systems more. As you learn to more about systems, it gives you the ability for you to restate that purpose to change with your questions and answers. So we're going to talk about all three patterns as we go along, both on real-time, micro-batching, and batch process. So on the real-time and micro-batch, if you look at it, the main distinction being with the real-time or the streaming system, the idea is that you are responding to a single event which is happening within your stream. For example, let's say if you're a payment website, every transaction which is coming, it's important for you to respond to every single transaction at that point in time to know that whether transaction is, let's say you want to build a fraud monitoring system, whether transaction is fraud or not. But on the microbatch side, the idea is less about being able to respond to a single event, but it is more about being able to respond to a group of events on a small interval. The small interval could be minutes, could be seconds, or whatever be the need, or based on that idea. There are 3 different processing systems we're going to talk about in that context: Kinesis client library, Spark streaming, and Apache Storm. So starting with the first one, the Kinesis client library, once you write your data into Kinesis, to process it, as we mentioned before, there are multiple things you need to understand of. First, your application has to scale up and down as your number of a shard grows or shard shrinks. You have to be able to recover from failure. You have to deal with checkpointing. You have to make sure that each and every record is getting processed within the worker. So what KCL does actually is KCL takes away all of these problems away from you, so you can focus on your record processing logic. And KCL can handle elastically scaling based on your number of shards, making sure that any records which are being processed is getting checkpointed, and in case any failures happen, it can automatically scale up or scale down with that. And that's what really KCL helps you building a distributed processing system on a streaming data set in Kinesis. How it really does is that within KCL, you have first a worker, which is illustrated in the previous slide, a worker being a unit of a process which runs on within the context of a KCL application. Within each worker, you create record processor. And what the worker does is it assigns a record processor to each shard. So worker will take the data from a shard, give it to a record processor for the shard, and also keep checkpointing the data set back in a DynamoDB table. The name of the DynamoDB table is the name of the KCL application itself. And that is what is used for checkpointing to help it recover also from failures in case that happens. And in this model, all you need to do is basically write your application logic in the record processor, and the KCL can take care of running that at scale, running that elastically with your Amazon Kinesis stream. Further along that, built on top of KCL, we also have connector library. The connector library allows you to use services such as Amazon S3, DynamoDB, Kinesis, Redshift, and also Elasticsearch. So you can use the connector library to write data to any of these streams. And the various use cases could be, for example, you could have a simple KCL application or connector library application, which is archiving your data to S3. There could be another one which is doing a microbatch loads into Redshift, or doing a real-time monitoring metrics extraction and writing that back to DynamoDB or something of that sort. And each of these connector library gives you a further much easier pattern, a much easier boilerplate template code you can use to build your application processing on top of AWS using Kinesis. Amazon EMR, which is a managed Hadoop cluster in the cloud on AWS, which also gives you the ability to have run familiar tools within a Hadoop ecosystem, such as Hive, Pig, MapReduce, etc., to take the data and run something like SQL queries using Hive on top of a Kinesis stream. It's as simple as basically creating a table on top of Kinesis stream using the input storage handler we provide. So using that, you can just basically start running simple extraction jobs on top of your Kinesis streams on a certain microbatches interval, on a small intervals of data itself. You don't really have to do anything. You can just use your familiar expertise that you have in-house to deal with working with tools such as Hive and Pig, and apply the same principle on top of a data stream such as Kinesis without doing any underlifting work in there. Just a brief introduction to Spark streaming. For those of you who don't know about Spark, it's basically in-memory compute framework. The basic principle behind Spark is something called RDD, which stands for Resilient Distributed Data Sets. Think of it as a partition data set across the nodes of memory in a cluster. And what Spark streaming does is it allows you to basically apply operations in parallel on those partitions by the RDD. The Spark streaming goes a step further by having microbatches of RDD created in something called a group of RDDs called discretized streams or D streams. And any operations you can apply in principle on RDDs, the same operations you can apply now on D streams, and that can give you a better way to run your operations across the streaming data sets. The second one being Storm. Storm is a stream processing framework The basic unit of processing behind Storm is something called a topology. Topology is basically a unit of work which runs on a Storm cluster. Within topology, you have something called a spout. In this case, a Kinesis spout, which is going to read data from Kinesis and play into the Storm topology. And the bolts are one which are going to do operations on the records coming in or on the tuples coming in. And bolts can do work like counting, processing, filtering, and etc. And any sort of the window which, any sort of processing which Storm can support. For both of these, for the first one, there's a Kinesis receiver available with Spark 1.2.1, I think, which you can start using with Spark streaming. And for the Storm, we have a Kinesis Storm spout available in GitHub, and you can use that as a pre-built spout for you to replay your data within your Storm topology. In the end of it, as we mentioned, just to put it all together, that you will have multiple patterns of data sets coming in, and the idea being that first you're using different processing paths with Kinesis data sets to do different things. First being that you could write a counter back to a real-time counter or monitoring counters in DynamoDB, so your application can display a real-time dashboard, etc. You can even use that KCL to do a microbatches load into Redshift, so you can use your extracting BI tools or extracting in-house visualization tools to look at the data in a more timely manner. And the last one being that you can accumulate your data in S3, and you can use something like EMR to do deep learning, machine learning, build your fraud models, etc., and push that back up to into DynamoDB tier, so your application can react in real time to when you come to determining whether transaction should be allowed through a fraud system or not. And those are some of the patterns you can build together using Amazon Web Services with Kinesis for doing a real-time analytics on AWS. And finally, to help you get started, we also have AWS Big Data blog. There are a few blog entries which can help you with learning some of the processing you can do with Kinesis. For example, they're on how to use a Lambda function, how to use a microbatching load and workload to Redshift with Kinesis, how you're going to build a sliding window application using Kinesis and Storm. And I'll encourage you guys to go take a look at some of these blogs. And these are the patterns you can help build basically to get started with real-time analytics on AWS. With that, I will invite Kandab to talk about GRI further.
Thanks, Rahul. So just a little bit about GRI International. We are a global gaming company headquartered in Japan, and we started our Western operation in San Francisco in 2008. Since then, we have released like several titles, both in Apple Store and Google Play Store. Some of the titles we have are in top grossing category. So why do we need analytics, right? We have like all of these games, and we want to like constantly improve player experience for our players. So to improve that, in order to enable us to improve that experience, we keep tracking of like player activity within the games. So we have all of this game data coming from the game client and the server. We also have like some user tracking, user interaction that's happening on the screen, client screen. We collect those data as well, and some of the performance data for our game services as well. So we take all of those data and constantly try to improve player game experience. In addition to that, we run several marketing campaigns to engage more players in our game. And all of those campaigns, we want to keep track of like user click data and downloads, application download data. And all of those data help us like enhancing our marketing spend for marketing campaign that we run. And in addition to that, we want to like also keep our player engaging. So we have this player targeting data and other game events. And so that can give us a good idea of what's going on within the game ecosystem. So from very beginning, we started as a data-driven company, and we collect huge amount of analytics data from throughout all of our games. Some of the sources of the data that we collect is like mobile devices, game servers that basically serving our web traffics, then ad networks that we partner with. So we collect all of this data and then we analyze those data. If we look at our overall data volume, it's 500 gigabyte a day, and in overall, like we have 500 million plus events that we are generating throughout our titles. Average size of those events are 1 kilobyte. Also, this is how our analytics data look like. We decided to go ahead with the JSON structure as a schema-aware format for all of our analytics data, and that helped us a lot throughout our various tools that we build. Having schema-aware format for analytics data allows us to like run EMR jobs or process it in whatever way we want to do. Help us a lot. In addition to the actual game data or event data, we also have some metadata that's attached to each event. Some of those metadata are like what database this event is going to, then what's the actual event name when this event gets generated, and we create like unique ID for each event. So those are some of the example of metadata that we have for each of our analytics event. So before we started working with the Kinesis, we had our in-house analytics data pipeline to collect and store all of this data that we were generating. But as we started adding more games and our player base started increasing, we started to kind of getting into the managing issues of this analytics data. Some of the key requirement we had is like we want to be able to like do guaranteed data delivery. We want zero data loss and corruption, and we want to be able to add multiple consumers easily. It can be a consumer for like just storing data and then forwarding it to any data warehouse, or we might want to like just do real-time aggregation on stream of analytics data that coming in. So whatever analytics pipeline we had, which is developed in-house, like we were trying to get into scalability issues when we try to add more consumers. And also, like as we started analyzing this data more and more, there are also requirement in order to like do a real-time analysis. So real-time latency for analytics data was also started to be getting important for us. We also want to be able to do like real-time ad hoc analysis on top of our analytics data. And we wanted this service to be a managed service because we believe that we should really focus on developing a game and not managing this data pipeline. So having a managed service like help us focus more on building tools on top of this data so we can give better results. So after converting, after started using Amazon Kinesis, this is our analytics architecture. So our game client sending data to game server, there are also events generating from the game servers, and that data is being forwarded to Amazon Kinesis. We have sender install on each game servers, which forwards any analytics data that we generate to further in the pipeline. Here in this case, it's forwarding data to Amazon Kinesis. From Amazon Kinesis, we have multiple consumer applications that processes data out of the Kinesis. One of the consumer we have is a simple store consumer, which stores data into S3. And once we have data in S3, we load that data into Amazon Redshift, or we run EMR jobs on for doing more deeper analysis on top of that data. So that's pretty simple consumer. If you look at so we built this particular consumer and whole pipeline using only 3 to 4 engineers and in really short amount of time, like 4 months. And that was a really great win for us. And initially, we ran this in-house pipeline and this new pipeline in parallel, and we made sure like we have all the data integrity and other things. In addition to S3 consumer, we also have a consumer for calculating a real-time stats within the game, and that one is doing real-time calculation and storing data into Redis, and from there we display that data into a dashboard. So let's talk about like some of the key components of that analytics architecture. I mentioned before that we run Kinesis sender on each of the game server, and just to be on very high level, like what that sender does. This sender is hosting on the game server. It connects to Amazon Kinesis stream. It reads like how many shards within that particular stream. As Rahul mentioned before, there are multiple shards in the stream, so sender needs to know like how many shards it's sending data to. Now, all of our analytics data that we generate, we store it in a file, local files, and that local files is being consumed by the sender on the machine. And so sender keep reading those files, and it create the buffers. It also compresses that data, and once it reaches the limit of 50 kilobyte, it sends that data using Kinesis put record calls to one of the shards into Amazon Kinesis stream. Now, here, if you noticed, we are doing a compression as well. It might be a heavy processing, so depending on how you are sending data, you might want to not compress your data and just send it directly. As we have decoupled the process from data generation to sending. We are doing compression here, and it's totally independent process, and because of that, even if we do a compression and it's a little bit heavy on the CPU, we aren't worrying about that much. But like doing compression allows us to like send a larger chunk of the data greater than 50 kilobyte. Kinesis has a limit of 50 kilobyte, but if we do compression, we can send more data. Now, most of our events are 1 kilobyte, but there are cases where event can be larger than 50 kilobyte. For an example, we store client crash log events, which can easily be greater than 50 kilobyte. Doing compression allows us to send more data, so we can still send the crash log event through the same analytics pipeline. So some of the design choices we made while building this sender, as I told before, that we have multiple titles, and we could have gone with the either single stream approach or stream per game. In our case, we choose to go with the single stream because management of single stream is easier than managing multiple streams, and processing that we were doing on the other side, consumer side, was fast enough in our case, even with the single stream. So we decided to go ahead with the single stream in our use case. Then you can either do a batch events, or you can do a single event. Now, we have our analytics data is like on average it's a 1 kilobyte. If we do a batch events, we can send like more events within the single call. So we do a batch event, and we also have the decoupled process. So it allows us to like do those buffering in independent process. So we are using batch events. Then compression, and should we use compression or not? So as I mentioned before, we are using compression, so we can like send larger events. It also allows us to like send more data within just single call. Another thing you can use, like, should you use partition key or explicit hash key? Now, if you are doing, depending on your application, you might want to do a partition key if you are doing aggregates or other kind of things that so you want to make sure that the same player data falls into the same shard. So you might want to use a partition key. In our case, we are using explicit hash key because we want to minimize our resharding strategy. If you use a partition key, you might end up doing like resharding a lot. But if you use explicit hash key, you can like evenly distribute load to available shards within the stream. So next, we're going to talk about the consumer, which is a very simple store Amazon S3 consumer. So this consumer stores like, so we are using KCL on the consumer application. As Rahul mentioned before, it helps you to helps you with the resharding that might happen within your Kinesis stream, and it takes care of most of the task for you. For example, you are seeing here two consumer processes processing data. But if you add more shards like KCL library, make sure that it creates any necessary worker in order to process that new shard. And at the same time, if you take out any shard from your stream, that particular worker will eventually stop processing data, and you can free up that resources. So using KCL allowed us to like build this overall system like very rapidly. So KCL, all it does like it emits record for you. So whatever data you are putting in using the put record in Kinesis, it provides you that data, and then that data you can use it whichever way you want to use it. So for in Amazon S3 consumer, as we are compressing data, we do a decompress first. We also checking for the duplicates here once we do a decompression. The reason we are checking for the dedupe is like because when you do a put record call to Kinesis, it might be possible that you received HTTP 500 response. And whenever you receive this HTTP 500 response, you are really not sure whether that data you send it to Kinesis made into the Kinesis or not. So because of that, we have to retry that particular data that we sent. So in that case, if that data already made into Kinesis before, we will end up with the duplicates. So we find this out after initial like testing phase, and that's why we introduce the dedupe phase in the consumer. Once you dedupe, we divide that data into a target table. The reason we are doing it here because it's we are sending probably 1,000+ events within the same stream. So we need to know like which data, we need to divide that data and then do a validation to make sure the data formats and data types are valid. And this data is primarily used for loading data into Redshift. We are doing validation based on the schema we have in a Redshift. So after validation, we do a DSV transformation. It's just a delimited format that we use for loading data into Redshift. And once that happens, like we again buffer that data up to certain size or timeout occurs. And from that, that data goes into S3. We compress that data again and store it into S3. We also, at the same time, we also make a pointer to that S3 file and put it into our file metadata DB storage. And that pointer basically helps us to load data into Redshift in the later phase. So that's our simple S3 consumer. So let's talk about the loading data into Redshift. Now, so as I mentioned before, like we have this file pointer into S3 that we want to load data into Redshift. So we start with that metadata DB, and then we open up a transaction, and then we get the list of pending events that we want to load into Redshift. So from once we get the list of pending files for a particular event, we create a manifest file that goes to S3 again, and from there, using that manifest file, we execute a copy command on the Redshift cluster. And once you execute a copy command, it will get back to you with the like status of that particular copy command. So we do that in a batch mode. So every transaction like loads data 10 or 15 events at a time. So that basically multiple events in one transaction. Now this is something like not usual. Like you don't need to open up a transaction here. The reason we are doing a transaction here is because we have the way we have structured our data into Redshift. We have 1,000+ events for all of our titles. Now some of the events are same events, but it has like some additional data. So for an example, like one game has a level up event and another game has a level up event, but it still count as a like two separate event. And those events might be differing, like some of additional data or like some additional columns that they have. And because of that, we ended up with like 1,000+ tables that we need to load. So when we have that many tables to load, to be able to do efficient load in Redshift, we are using transaction. So at the end of the transaction, we update status back into the metadata DB, and that way we know like next time we run that process again, we know that that file has been already loaded. One of the reasons we are using metadata DB, so we can bring up actually another cluster for any ad hoc analysis that we want to do. So in order to provide ad hoc analysis on additional Redshift cluster, we can just use this metadata information and then load even one table on a totally separate Redshift cluster. So the next thing is like consumer real-time stats. So this consumer is primarily function to calculate the real-time stats from the Kinesis streaming data that coming into Kinesis from Kinesis. This consumer is pretty much same to the S3 consumer. So it's doing like, it's using KCL, it's using decompression, it's using like dedupe, and then it divides that data into target table. But from now here, like it takes configuration files. So we have a configuration file that let us know like which event we are interested in. So we filter a number of events based on that configuration file. We have 1,000+ events, but we might not be necessarily interested in all the events. So based on the configuration file, we might be like only processing 10 or 100 events. So it uses that for filtering an event. In addition to that, it also calculates like data based on the configuration setup for each metric that we want to calculate. It uses that configuration again to like calculate the metric segments, like what's the value for that particular metric and segment, and what's the time slot. And from that data goes into Redis again. So data goes into Redis, and we have built a dashboard on top of the Redis, so we can see in real time what's going on within our game. So that's a real-time stats consumer. Some of the lessons we learned during building this Kinesis pipeline. It's always a good idea to like decouple your data generation part from your sending part. That allows you to do like multiple things. You can buffer event, or you can batch event. If you need to do compression, you can also do compression. And in case like and decoupling your sending part also allows you to like not worrying about your actual application latency, and just you can focus on your actual data generation in separate process. Then batch and compression if you want to send more data in a single call. Put record HTTP 500 can result in a duplicate. That's why we have introduced dedupe process in a consumer. Also, like we recommend like monitoring some of those events. When you send a When you send data to Kinesis using put record call, it comes up with like few error message type. One of the error message type is like provision throughput exceeded. If you start getting a lot of those events, you might want to like add more shards, because what that means is that you have more data to send compared to number of like shards you have available in the system, or your shards capacity in the system. On the consumer side, it's very recommended to use KCL because it makes your development really fast, and it takes care of like resharding mechanism or checkpointing your data within each shard. So that helps a lot in expediting the development process. Always autoscale and monitor your load on the consumer application. That will also give you an idea of like adding more shards if your consumer is falling behind compared to like how many what amount of data you are generating within the system. In overall, provision enough shard when you start working with the Kinesis stream, and you can add more shard as you go. Handle your shutdown gracefully in both consumer and sender application. It's very important that you handle shutdown gracefully and do a proper checkpointing. So that will help not generating duplicates for your system, like for your data. And in the last, like follow AWS best practices for error retries and exponential backoff. Some of the takeaways from the system. Kinesis in general, like it's data, whatever data you send to Kinesis stream is available for processing within the seconds. So that allows you to like build your real-time application. One of the things Rahul mentioned before, that you can build your real-time monitoring on some of the transactions. So for an example, if you want to like see if that particular transaction is a fraudulent activity or not, you can do such things using Kinesis. They have pretty robust API, and there are lots of libraries available as well to help you get started. KCL, and there are connector libraries for S3, Redshift, and EMR as well. So you can, so that connector library can help you on the consumer side, and you can just plug that library in, and it will send data to S3 or Redshift, whatever data source you are providing. In general, AWS, it's always good to have a managed service compared to like managing your own cluster and spending time in that infrastructure. Scalable and very cost effective in general. Yeah, so quick to get up and running. We actually build all of this system like in 3 to 4 months with very small team. So from that you can take an idea of like using Kinesis, like how quickly you can build this analytics data pipeline, and that scales automatically as your volume grows. Thank you all for listening to us, and
thank you everybody for attending.